Okay, so finally, found a little time to continue doing this hash table implementation. So right now it's a little naive. There's a lot of like, let's say, missing things that can be done. Of course, I will be try to do those enhancements incrementally. Um, right now it's also extremely late. Well, not extremely late, but kind of late. So I'm just gonna try to keep this short to approximately 1 hour. Um, Yeah. So one of the things I want to kind of start with is that I also have noticed that I haven't been paying so much attention to actually the length, and technically speaking, the length of the hash tables should always be like a prime number, and that's because basically the when we're hashing, when we're doing these hashes, the prime numbers helped to find like evenly spaced integers in the basically in these slots or buckets. So that's one of the basically the main reason. And I also wanted to kind of just go back to this hash function because essentially this hash function is called I think double hashing. Yeah. So yeah, and basically it's this formula here, right? So there's two hash functions, h1 and h2. So here we have h1 and h2. um, so yeah, so basically they also have to be distinct, right? So the first hash function, so I use, of course, like what I did last time was using this native hash fnv that's in the standard library in Go, and that creates, of course, a hash of a key, and it's non-cryptographic, so it's uh, much quicker than cryptographic hashing algorithms. So for that, I take the first one, that's hash key modulo length, right? And that basically keeps that hash index to be in the bounds of the array, so from 0 to basically array length 0 to n minus 1 or size minus 1. And then hash 2, which is basically this one here, h2, which is basically takes the same hash key, and then obeys this principle here that it should never yield an index of 0. So basically that's why we're adding plus 1 here. And then this thing here at the bottom in line 45 is basically all of this stuff here. Um, so we have I, which is basically like the collision count, and then we multiply that by hash 2, and then we mod by the length of the array this has. Um, and then the other thing that is very important um, is that it has to be relatively prime to the size, right? So that basically means the size has to be also a um, prime of the hash table. And that's something I've not really paid attention to. And that's basically something I want to start to change at the moment. So what I want to do is getting the like some pre-computed prime numbers. So just to speed things up, I did find like a nice page that has that. So pre-computed uh, hash table um, primes, pre-computed good hash table primes. Okay, so yeah, this is what I was saying. Prime numbers are typically used to keep collisions uniform when the population being hashed. So it's okay. Yeah, so it's to keep basically the all the elements inserting the array more like uniform, so to speak. But I'm not 100% sure if that's really so possible in practice. But I'm not an expert also like in this type of like hashing algorithms and all of these that more let's say mathematical um, concepts required to like fully understand it. Um, so I think this is not how I so pre-generated. I think it was hash kilograms. So okay, not finding it. Ah, here it is. Oops, I missed it. Yeah, it's this one actually. So I think I can store this in an array, and then I think the last number here is like a size of 1 billion. So I think that would be enough. Um, One thing also to take into account that I'm not gonna really pay attention is when to stop resizing, and of course it can be unbounded. What one safety measure will be the basically what is the largest integer in Go, I guess, and if the length is basically equal to that, we basically can't resize anymore, resize up. So I'm just gonna take this thing, go to perplexity, and create go array of these prime numbers. Let's see if it gets it. Not sure if it will. Probably not sure if it will understand the format. Would it? It seems it did actually. Nice. Okay. Okay, I have to stop this a little bit because my wife is giving me a call. So, okay, nice. So I hope I'm recording. Yeah. Ah, cool. So let's continue. Small interruption. So I'm gonna go here and let's see, 28, 25. Yeah, yeah. Okay, cool. So I think it did pick up all of them. I'm just gonna say, yeah. Well, I'm just gonna copy this. So cool. That's actually another cool use case for LLMs. Kind of dumb, but just to also make formatting easier. Saves a lot of time. So okay, so I'm gonna add this and const. Does it need to be probably? No. Okay, some syntax stuff. Um, does it need to be this? No. So, well, I don't know really. I don't know the syntax here. So I'm just gonna come here again. Fix syntax. Okay. Const does not suppose concept or slices. A const keyword can only be used for basic types. If you want an immutable array or slice, the closest idiomatic approach is to use the var keyword. Okay, fine, fine, fine. Okay. Okay. Cool. So. Okay. So now this should be. Um, I think I should have like some internal method here, like pick size. um, pick length, I would say, and UN64, UN64. Okay, so I have to pick the length. Oops. Okay, so I'm gonna go so for can I do? Let me see if I can. If I have the range keyword here, I can say total items. Did I ever use the range keyword here? Forgot the syntax as well. The thing is that I'm still also kind of still learning Go here on the while I'm implementing this. You know, this will basically work, which is primes. But I also would like the range. So let me just take a quick look here at the Go range for yeah. I think this is what I kind of want. It's a little cleaner, little cleaner. So range primes, and I really need this thing here. So then here I can say, oops, I can say if length is, what would I say, smaller than or equal to? So yeah, probably larger than or equal to um, v. Yeah, of course it's mismatched types. So I have to change up the stuff up to UN34, UN64. Return, we return v prime. So I need to make this UN64, UN64, nice. Okay, so basically it goes through all of the primes and then the length, if it's larger than or equal to the first thing, right? So essentially, if so for example, I don't know, if I choose 100, it will be, so if 100, so it will choose 193. And if I choose, for example, like 1,000, it will choose 1543, like the first one that it encounters the largest. Yeah. Okay. So okay. So that is that. So here, I want to call this, but perhaps just maybe. Yeah, I have to add here. So if it can't find I need to throw an error. And I think I'm gonna just panic. Panic. The length you provided, yeah. Can I say panic? Yeah, it doesn't say. Okay. The provided length is not supported. Cool. Okay. So I think that's it. So and I think yeah. So what happened? Okay, yeah. It's unused. So here I wanna basically do yeah. So I wanna say prime length. Prime length. Oops. Equals to pick length. And we have the length here. Prime length. Nice. And prime length. Okay, nice. So that should work. And I hope also, okay, if I run go, what is it, go test, that the benchmarks I have initially won't run. So I don't want to take so much time. The provided length is not supported. Yeah. So I made a mistake. So if this value is larger than or equal to length. Nice. So yeah, length 53, but it should be 10. Okay, so it's this is good. So it's failing. So this yeah. So I think target length, and then I have to say actual length is 53, right? So this should be actual length, and this should be now passing. Okay, so resize up. Okay, I'm gonna comment these out, up, down, for the time being, or I'm gonna leave them. I'm gonna leave them. I'm gonna leave them. Just failing for now. Just failing. Nice. So I have this, that. Okay. So yeah, this is working here. Okay. Um, But I think also I need one for resize down as well. One for resize down. Okay. So resize, insert, insert. Okay. Yeah, and then I have here resize. So I have here also I have to say pick length, and then I'm gonna say h dot length times 2 new length. Okay. So the problem here is that this pick length, of course, picks the next one up. Now, just by virtue of that, let me, oops, let me fix this function. So this, yeah, I can just say, oops, maybe this will be called desired length or sure. Uint 64. Okay, so 10, so 53 is the actual size. So 53 so it's gonna be 53 times 2, of course is 106. And then the next biggest size should be 193 on the resize. Ooh, I think this is gonna go short. Ooh, this is gonna go short quite easily. Yeah. Anyway, I'm gonna continue. So what did I say? 109. Did I say 190? 93? Yep, 193. Okay. Okay. Also forgetting the shortcut to move. No, it's not this one. To move complete lines. Okay. So this is going to be expected length. So I can delete this. And I'm going to say, no, this is going to be actually, no, expected length. This should be named expected length as well. Okay. So let me run here the test. Yeah, so this didn't trigger the resize, of course. So hash table length is 53, and so and also the load compute load factor is occupied slots divided by length, right? So and that has to be, let's say, 15 divided by 53, 0.28. That's not going to trigger it. So let's say 20 or 30, perhaps 30 divided by 53. No, 35 divided by 53. Okay, so let's go for 35. So this should trigger the resize. Um, Perfect. So that's fixed. Now let's go to resize down. Resize down. So um, highest. So I'm just gonna say highest. And highest, right? Or otherwise, if v is smaller than or equal to length, right? We will immediately say return b. And of course, this should be redundant here. Should be the redundant, but we can keep it just in case. Yeah, no, actually it's not redundant. Okay. So here by default, I'm gonna have highest, it's gonna be true. True, okay. Delete, and then we have this one here. Um, okay, nice. And now resize down. It's gonna be the same thing here. So expected length, so 53. So we're gonna say 53 divided by 2 is 26. So it's gonna be 53 again, but I want smaller primes as well. I need smaller primes. So prime number list. list of prime numbers. Here I go. So just for the sake of it, so I'm going to say 11, 17, 17, and 23, 23, and let's say 37. Let's say 37. Okay, nice. That's it. So if I, but then my test will, yeah, the other one will break. So just for that, I'm just gonna say the size I want is now 40, and the size I want now is 40. So it goes to that one, and this one as well. I think 40, so it goes to 53, and then 26.5. It will be 37. Okay. This might be, maybe will fail. Maybe will fail. 168. Not enough arguments. Ah, yeah, of course. Yeah, yeah, yeah. Highest. Sure. Okay, test. Okay, so filling here again. So to do that, I want to say 17, just 10, just 17 here. Fine. Now let's go to resize down again. Hash table length. Hash table length 26, but expected 37. Yeah. So the resize down. Resize down threshold is 0.12. So And right now the length is 53. So I have to say 3 divided by, so yeah, I mean I can say 3 here for example, and I think that should figure it. Length 26. Okay, this is weird. Why is this doing 26? So the higher length is 40, it should be 53. Yeah, 26, 53, 26. Ah, I know why. Ha, Jesus, I forgot to do this. Oh, oh my god. Okay. Yeah, so it chose 17. It chose 17, of course, because 53 divided by 2 is, of course, 26. So here, this will be 26. And then it will choose the first one that's smallest, which is 17. So this needs to basically iterate backwards. This needs to iterate backwards because if not, it will always pick this one, this smaller one. So you should always pick like one size down. So 53 smaller than 26, well, 37. So 23 smaller than 26, yes. So you should pick this one. I think so. Yeah. So do the same thing for now. Same error message. Okay. So I think this should do it. Yeah. 23. Nice. Okay. Whew. Whew. Nice. So yeah, active slot counter 012. So yeah, active slot counter because we deleted one, right? From three, so two. Fine. Nice. Okay. Oh, so that is done. That is done. Yeah, this will run out very quickly, but I'm gonna just have it for the time being, and I'll worry about that later. Oh, nice. So I also did I didn't do the benchmarking stuff yet to run a specific test. Okay. So yeah. Okay. Yeah, I'm gonna see what happens. So go test run. I forgot the benchmarking stuff. To be honest, let's review here. Um, go bench. I think I went to this one the other day. Testing flags, and we also go say go help test. Nope, it's not telling anything useful. Let's go back here. Bench. What's it called? Bench or B flag. Yeah. Okay, yeah, here it is. Bench. And then I was using another one, which was this one, bench mem. Okay. Okay, cool. There it is. So I'm gonna add this here. Tests. Done. And okay. Okay, there it is. Okay, cool. So okay, so there is one thing I need to do. Search existing key, benchmark non-existing key. So I want to also test this inserting a bunch of stuff. Inserting a bunch of stuff here. So okay, so func insert, and also without resizing. No resize. Okay. So one thing I want to do is here, like set up the code. So do some setup here. So I'm gonna say make. There's gonna be an array of string, and it's gonna have some size. And I'm gonna say total keys maybe like let's try 1 million perhaps. It's 1 million. The range syntax again. Yeah, and oh, I need to also modify this one. Just forgot about it. So okay, so total keys, keys, hope, Why is this doing this annoying thing? Why is it saying total keys? That's really annoying. Okay, but actually, I don't need this. Can I do that? Yeah. FMT dot sprint f, and then we have the famous one and only foo. Foo. Okay. Ah, nice. Cool. Okay, so this is the setup code. So I have a million things. Mm, okay. Um, and now I have to do this loop thing. So let me go back. Ah, yeah. I have the older version of Go. So let's try this. Yeah, bn. So now I'm gonna say dot stop timer, and then here I'm gonna make the table new. Let's see. So I'm gonna just make it. Mm, I think 2 million as well. So um, table size or length to be consistent. Uh, oh, yeah, I should actually. Oh, just do this. Okay, and then oh yeah, oops, but I now have to loop through keys. So for um, key. Okay, so table dot insert key. Okay. And then I'm gonna start the timer here. Okay, so stop the timer to create the table because I don't want to measure that. And then start the timer again to basically time all these operations. So a million inserts. So I think, yeah, I think it shouldn't resize. So just to maybe just verify. Uh, okay, so I want to just run this single test. So man, I think this should work. Yep, nice. But it's no, it didn't. Okay, but it didn't resize anyway. Okay, so yeah, as expected. Oops. So why didn't this work? Ronald benchmark use bench or let's see if this will like it maybe. Yep, I think that was it. Now just to experiment one more thing. No test to run. Okay. Okay, let me see. Okay, so I think this should be it. I'm gonna add this here. Okay. Okay. Okay, nice. So I have this. So nanoseconds. Okay. So let's see. Just to have the conversion. So nanoseconds to milliseconds. Okay. So I think this is over. I think, yeah. So what it is that, like, on average for 1 million insertions on a hash table with 2 million, with the size of with 2 million slots, it's 255 milliseconds, and I don't know if that is very big, very fast or not. Not 100% sure. Not 100% sure. So then I also want bytes to, I don't know, megabytes perhaps. Bytes per operation as well. Well, why does it say 65 megabytes? That is a large amount of data. So all of that was operated for a million, was allocated for 1 million inserts. 1 million inserts on average over 4 runs that this thing was ran. Wow. So that's crazy. Okay. I don't even, yeah, right now want to check for the resize part. But there's one interesting thing that I want to basically also do. Okay, so I'm gonna park this for now here. So I think one of the yeah, but actually before I do that, let me just say pick. So this can be basically removed. And let's go here so I can delete this thing. I think that's all. No more references. Yeah, this one. Okay, nice. Okay. So yeah, the other thing I want to do is I remember last time, so I drew this thing here. It doesn't let me open it. What the hell? Let me see. Open with paint. Let's see. So last time, one of these videos, I was kind of explaining this. There's one thing that I think was kind of confusing here. I don't remember what I exactly drew here, but there is one thing just to clarify. So here I was mentioning that right now we have like pointers to the actual objects, and I was mentioning also like that can produce even more cache misses. So the thing with hash tables is that they suffer a lot from something that's called, they have bad data locality. So I cannot write with my mouse, it's going to take too long. But basically, let's say DL, right, data locality. Let's see here. So data locality is basically means how close in memory or is data stored, right? So basically adjacent in memory. So one of the things that arrays are good at, so for example, like let's assume, this is, I'm just gonna expand this thing, that our arrays per definition are good at is that they have good data locality, right? And what that means is that their values are basically stored in contiguous memory blocks. Yeah. So like there's one value here, one value here, one value here, blah blah blah, and then of course they all have like certain memory addresses, and by allocating, let's say, like for example, I don't know, in C, we have to say the size of, let's say if these are structs, the struct, right, with malloc, and then that gives us basically plot times the number of things we want to allocate, right? So we want to allocate, for example, I don't know how many things we have. 1, 2, 3, 4, 5, 6. We have 6 things. We'll allocate one large memory block. Yeah. And then what? Why it also it's good, like let's say the thing with data locality, is that, and I also kind of briefly mentioned this in the other video. So modern CPUs have like caches, right? So we have L1 cache, we have L2 cache, L3 cache, etc. And basically, these things were done to basically speed up memory access, right? So because RAM is extremely slow, so basically, like if we have our um, maybe this is not such a good drawing. So okay. So if we have here, for example, one CPU, right? CPU, and then let's say here, over here is like, over here, let's say is RAM, and then here we have like the different levels of the of caches, right? So we have like that one, then we have the other one here, and something like that's the other level. So in fact, I'm gonna just open CPU caches L1. Yeah, so this is basically the thing here, right? L1 and yeah. So of course, each CPU will have its own L1 and L2 cache. Didn't know L3 cache was also shared, but whatever. So yeah, so basically this is the locality of reference, right? Caches work best when your program exhibits good locality of reference, right? So this is the thing I was talking about, spatial locality. This refers to the tendency to access data located near recently accessed data. Okay, so what that means here is, can I take a screenshot so I can draw? Yeah, I'm gonna take a screenshot of this easier, so I can draw over this thing. Edit and paint. Cool. Yeah, nice. Much easier. So basically, when the CPU first basically needs to access data, say when when a program first starts, nothing will be in these caches here. Primarily, we'll look in L1, I believe. It's the closest one to the CPU. So it's always like for much faster, basically data access. So when the program first runs, it will try to say, oh, is there like is this variable that my code is referencing is data stored in memory? It's not, so it'll be a cache miss, right? It'll be a cache miss. So then it will have to go to basically main memory here to RAM, which is like slow, right? There's also some like charts as well. So it's slow, right? But then after that, it will load into the cache. It will load straight away into the L1 cache because, again, it's the closest thing to the CPU. It will load something called like um, a cache line, right? So it will load a cache line, an entire cache line, and then depending on the architecture of the machine, um, it's like either I think 64 bytes, right? 64 bytes. So it will load the entire cache line of the 64 bytes. And then that, of course, will include the requested data, right? So let's say this is the requested data. But then, let's say this is the requested data, but then it will also load other stuff, right? Like other data. Just because, like it's way cheaper to just do one trip, load a whole block, put it in the L1 cache, than just going like, oh, I want just this piece of data from RAM. I'm just gonna bring that piece of data. It will be very inefficient. So what this does is like in this basically cache line. So like these things are divided into high level in cache lines. Have like all the adjacent data as well. So basically, like if we are like in an array, right? We're in an array here. Uh, and let's say we're accessing this element here, it will look in the L1 cache and say, oh yeah, this thing I'm trying to access is in L1 cache, so it reads it straight from the cache, not for RAM. But then the nice thing is that once we're iterating over this element, the other one, it will also say, oh, is this thing in the cache line, right? And says, oh yeah, it is in the cache line, and then it will basically read it here, yeah. So that's basically what is referred to here as spatial locality, right? So in essence, an array is a cache-friendly data structure. Now the problem with these hash maps is that the data is like sparse, right? So the data in a hash map, so we have, let's say, our bucket or slot array as we call it. So it is an array. It is an array, but things are stored like in different places, right? So let's say this thing, and kind of like to keep drawing it to the bottom. We have more stuff. So it's like basically like a Swiss cheese. Like it's full of holes. So what that happens is that, let's say we're accessing this element here. So for example, in the code, if I go to like uh, search or even like insert, right? And I have this like, yeah, my home location, and I index it, right? Let's say it's this one here. Like most, that could be a probability that this thing basically is not on the cache, and it's basically a cache miss, right? And the same for this one. So that's why it suffers a lot from it's not a cache friendly basically data structure. And then on top of that, what I was doing, but I mentioned it wasn't a good idea, is adding these pointers, right? So then on top of that, like it has to hop here for the pointer, right? Um, let's say let's say in the cache line, and then that's a pointer. So we need to dereference that, and then actually hop to the real location, which then could be another cache miss. So it's like double cache misses, which is not so good. And also, I think we're at the same time storing more memory than needed. So hopefully, so I think this is going to be a wrap up for right now. So hopefully, if I remove this, this will be faster and this will be smaller. So let's see. Let's see if that is the case. So I'm gonna remove this, remove this. Nice. So of course there's gonna be some errors here. Um, one thing, yeah, one thing actually that kind of was thinking about this straight away. Would be nice. I'm not gonna do it right now, but would be nice to make this the integer as well. The integer as well, but for now, because it, yeah, for now, I'm just gonna say dot value. Why integer? Because I could say like if key, let's say if key is like -1, that would be quite handy as well. And then because in general, the key an integer will be I think 4 bytes, and I think it will, and I think how much is a string? So size of string in Go. Yeah, so the string, depends, of course, on the amount of characters, size, in bytes. It really will depend. It really will depend on the amount of characters. So if I have like huge strings, that is not gonna be so nice as well, because also the like as going back to the cache lines, the bigger these things are, so we're also kind of bounded by the value. Um, they will also not really fit properly in the cache line, so the data could like outgrow the cache line. And also these things are very very small, um, so they don't really hold a lot of data, like a couple of like kilobytes and stuff like that. Okay, so okay, nice. So insert, cool. So now I have here this one dot value. Okay, yeah. Okay. Ah, I moved this by accident. Okay. Okay. Nice. Oof. Okay. Okay. So that's finished. So I'm gonna run this thing again. Hopefully there's no errors. Famous last words. So what happened? I'm wondering why. Test resize down. My God. So why? What happened with this? Seems like this is broken. Delete. Mm. Okay, I think it's because I forgot to do this, perhaps. Hmm. Yeah, I think so. But I'm not 100% sure why it wasn't failing before. Hmm. No, but occupied slot. This is okay. This was a mistake. This one is definitely three, and then the other one. Okay, this is very strange. Ah, yeah, yeah. Okay. So yeah, three because this is basically four here, of course. So yeah. Or no, wait a minute. So system here. What? This is weird. What? That's so strange. Hmm. Okay, I'm gonna just leave this shit for now like this. Oof, it's also getting very late. So what was I gonna do? Oh yeah, run this thing again. Oh my god, and I should have also saved this. Ah my god, I should have saved this version, the previous one. Man, that was stupid. Let me see if I still have this one. Yeah, so it's 255 I had before. So I had 255 before, right? So I had before 255 ms, right? And now I have 222 basically milliseconds. 222 milliseconds. And memory used allocated 15. Oh, there you go. Well, still a lot, but so I think it still can be optimized. Um, MBs versus, yeah, basically 15.98, 15.98, 15.98 exactly. 15.98 MBs, right? So this is his with pointers to data structs with yeah. Wow, so that's yeah, quite an interesting thing. I mean, I thought it was gonna shave off even more. Um, that's 218 milliseconds, 222. Let's see if I can. What is this thing? Okay, seconds. There's like something here. What is that command like? Bench time T. So let me see if I do this 5 seconds. So it will create more iterations. Okay, this is 200 mil. Yeah, seems like then I can do these, run it even more, 9 megabytes. Okay, so it seems like I basically need to benchmark it more. Okay, yeah, interesting. 199 milliseconds. So yeah, I think I need to run it then for more time. That's what it seems. So this is 8.68. Yeah, interesting. Okay, so that's not bad, I would say. Okay, so I'm gonna leave this until now, but I think I'm getting kind of close, and would be interesting to see how many collisions. So I think with resizing, or maybe here, I'm just gonna I'm just gonna do something really quick. I'm just gonna do a small hack here, and then I will end this thing. I need to go to sleep. uh, collision count. Collision count. Uh, Win 64, and I'm gonna say for insertion. just like this. So that will basically count all collisions. I think, yeah, all collisions in total. So I want to count all collisions in total on inserting 1 million elements. So let me print this b dot log. I don't know if log, yeah. Total collisions. Oops, table. What happened here? Ah, of course. Okay, so let me. Yeah, it's gonna probably print a whole shit 58 stuff to screen. So for now, I'm just gonna do it the default, which is 1 second. Okay, wow, so it's always quite a lot of collisions. So let me see what will be the percentage. So if we have this, right, 199,019 divided by 1 million. Yeah, 19%. That seems quite high. Seems quite high. I'm gonna try again. Should be the same number of collisions. Okay, interesting. So I'm not really sure what's the collision rate I'm supposed to have. Really. So let me see something. I want to go back to. I think this would be the last thing because it's really getting very late. So there's another thing here as well. Enhanced double hashing. Okay, so this is like another thing we can add here. And then, okay, so let me try that. Power of what? Float 64 divided by 6. So let me see something here. I think I have to cast this thing again. Quadratic. What do they name this thing? Tetrahedral. Tetrahedral. So I think this should be it. I mean, quite redundant here, but just for the sake of it. Now I want to see if this will maybe decrease the collision count. I'm not really sure. Not really sure. Imagine if it increases it. It would be crazy. 198. It's almost the same thing. Mine is high. Okay, forgot to do this. Minus collision count. Okay. So float. Yeah. Okay, so I think this should be more like it. Okay, minus what collision count divided by 6. Let's see. The same. And even a little larger than this 198, 790. This is 798. 8 more collisions. So definitely this is right. Plus tetrahedral modulo length. Yeah, they didn't really improve it much. Okay, well, I think this is all for now. Now I yeah, just make sure. So this increased the time. So let me say 10s. Yeah, that probably increased the time a little bit. 205, 205 milliseconds. Yeah, basically the same. 205. Ah, okay. So I think this is it. Oh, kind of like a longer session than planned. Okay, nice. So yeah, I think I kind of did what I thought. It was a little spontaneous, but I think that's it. Okay, thank you so much, everybody. If anybody is like watching these recordings, yeah, I hope you enjoy it. Seeing me work through these problems, kind of live. And see you another day.